Hello and welcome to week number 2 for the PROC 2003 subject. In the week number 2, I'm going to cover a very important topic, which is going to be the engineering materials and their properties. And this will be the part number 1, and the part number 2 is going to be covered next week. So the very important question raised usually when we make a design is, what do we need to know about the materials we use? So when you're designing an engineering solution, do we actually seek for the material, or do we actually seek for the profile of the properties? So in general, material properties are going to be the currency of the material's worth. So trading one property against the another is the basis for the material selection. What is crucial is that the solution to a given problem can be framed in terms of the required properties. For example, require the profile of properties. If this profile can be satisfied, then the materials can be selected. The following two models are considered with the various properties that can be expected by the materials. Materials can be categorized into 6 distinct families. Within each family, there are broad similarities which related to the properties that are going to be exhibited and typical processing routes, and often resulting in applications. These families are going to be the metals, the ceramics, the glasses, the polymers, the elastomers, and the hybrids, or what known as a composite material. So we start with the metals. Actually, if you look around you, you can find the metals are going to be anywhere. So the metals are very frequently encountered metals family and have been used by humans for several thousands of years. Most elements of the periodic table behave as metals when isolated as an element. For example, the copper and the iron. Mixing metallic elements is called alloying and yields further materials within the metal family. For example, we have the brass, which is an alloy of the copper and the zinc. The metal's properties can be first a broad range of melting temperatures. It does have electricity conductivity that varying between one type to another, thermal conductivity, ductility and malleability, high yield strength, toughness, and elastic modulus. And metals are not transparent except under extreme circumstances, and a broad range of expense, and finally they are often susceptible to a corrosion. So as a summary, you can see that we have different types of the metals that are good conductors of the electricity and heat. It can have properties like bright and reflective on the surfaces. Malleable and ductile, can be molded, solid at room temperature except for mercury, have a high density and are heavy, forms cation in chemical reaction, and have low ionizing energy and typically solid at room temperature, as we mentioned earlier. Shear characteristics in the periodic table, and many are used in industry and construction. The other type is the ceramic. Ceramics are also very frequently encountered material family and typically result from the application of the high temperature to elements and compounds. The purpose of the applied heat is usually to support the chemical reaction leading to the high crystallinity. Many elements of the periodic table can be combined to yield ceramic, but the common varieties involve the metal reacting with the oxygen, nitrogen, and the carbon. The ceramic properties are very high melting temperatures, very broad range of electrical conductivity, poor thermal conductivity, very poor ductility and high Young's modulus, and brittle fracture, of course, tendency for the high hardness, a range of the optical properties from the opaque to the transparent, and also some of the ceramic are cheap while others are going to be very expensive. So these are different types of the ceramic. As you can see, they are under the application process, usually going to be made of clay or silica. Then they're going to put them at high temperature to sinter them, and also we can add the glazing to it to enhance the shape. There's a new ceramic, and it's going to have very high technical applications, are also considered in our topic. The glasses are solids that lack the crystallinity, and they are going to have a characterized as an amorphous. So away from having a crystals is going to be amorphous, and that's why you can see that most of the glass is going to be transparent. So this refers to the extent of the order within the solid, and in particular the absence of the recurring organization among the atoms. Tendency for the glass to form transparent solids leads to them to being frequently used as windows and containers. The formation of the glasses can be complex, but in principle the key features is the high temperature processing involving a high cooling rate. Glasses share many properties with the ceramic. The glass's properties are the moderately high melting temperatures, the poor electrical conductivity but can be made to conduct, poor thermal conductivity, very poor ductility and high Young's modulus, a brittle fracture, a tendency for high hardness, an optical transparency, and most glasses are reasonably cheap. So you can see here that we have different types of the glasses. Mainly we know that we have something called the annealer glasses, that they want to be heated treated by take it up to high temperature and then cool it down slowly. And we have the tempered glass, which is going to be actually heated up then cooled rapidly. And we have the laminated glass, which is going to be consist of multi-layers, including the gel in between. We have the soda lime silica glass, we have the aluminosilicate glass like the one we have in the phones, we have the fused quarters, and so on. Now we come to the polymers. Everybody have polymers around him, starting from your phone, your laptop, or many of the appliances we have at home, which have something in general we know it as plastic. So the polymers are a family of materials that are based on repeating subunits referred as mers. So we call it polymers because it consists of series of mers. The nature of the involved mer largely determines the nature of the overall polymer, but the variations can be achieved through the alterations to their local arrangement of mers. The result is a broad range of the properties and the ability to fine-tune properties to a large extent. Polymers are almost exclusively based upon the combination of the carbon and the hydrogen atoms, with the addition of the others such as the oxygen, nitrogen, and sulfur providing a specific functionality. Since they are based upon the carbon and the hydrogen, polymers are referred to be an organic material. So the polymers usually tend to first have a low melting temperatures, which is less than 200 degrees in most of the cases. Also, poor electrical conductivity can be made to be a conductor in certain cases. Poor thermal conductivity, low Young modulus module, and very high ductility, tactile to brittle fracture depending upon the temperature. Also, it have a broad ranging optical properties, low cost, and lightweight. So you can see here the different types of the link between the polymers and different products that we have for them. we can see that are going to be something like varying between the flexible and the brittle. One of the things that we had for a certain type of the plastic is the decay within the time, and that's what we can see, for example, here for the hydroxybutyrate. So that day one, and within the time it starts to decay until it's going to be a powder. Different type of the plastic, and I think that you use most of them almost daily. Now, away from the plastic, we have something similar that can also considered to be polymers, but we know it as the elastomers. And in general, in the public culture, we know it as the elastic. So the elastomers are technically a subgroup of the polymers, but are sufficiently large to deserve their own material family. What sets the elastomers apart from the polymers is their ability to accept a huge elastic deformation without permanently deforming. And this relates to the specific of the atomic bonding between the atoms and the molecules concerned. The elastomers tend to exhibit the low melting temperatures, poor electrical conductivity, poor thermal conductivity, very low Young modulus or extremely high ductility. Also, a ductile fracture except at very low temperatures, a broad ranging of the optical properties, low cost and lightweight. So these are some of the examples for the polymer for the elastomers. So you can see that the tires, the natural rubber consists of the loosey joint. Also, is going to be used as a base of the shoe. The hoses, the joints, and other stuff, washers, all can be done by using the elastomers. And now we come into the hybrid materials, or what you know as the composites, where the composites are a combination of two or more materials in a predetermined configuration that accepts a unique profile of the properties based on the exploitation of the favorable attributes and the offsetting of the less favorable attributes. So the hybrid can exist in extremely wide range of configuration or configurations actually. Some are highly technological and complex, such as the metal matrix composites, which consists of particles of fibers incorporated into a solid metals. Others are going to be a more conventional, such as the fiberglass or the steel reinforced concrete. In all cases, the properties of a successful hybrid are going to be high performing for a given design application. So the hybrids or the composite tend to exhibit the high cost, the challenging of in the fabrication, manufacturing, processing, and handling, and also again to have exceptional profiles of properties. The modern aircraft bodies and the car bodies and other applications are using the composite materials. They are light, have high strength. All the properties will be designed to add to a need. Okay, so this will make them actually a very important material in the family we have nowadays. The differences between the materials classes or families depends upon the difference in bonding between the constituted atoms. There are several ways in which the atomic bonding can occurs, and these can be considered as a primary or secondary. So the primary intra-atomic bonds, like the ionics, the covalent, and the metallic, and the secondary interatomic bonds like the van der Waals, the dipoles, and the hydrogen bonding. So this video can be found actually, both videos can be found on the Canvas page, on the view page. I prefer that you can watch them from there because usually we're going to have problem with playing them here. The atomic bondings and the electronegativity can be found in the periodic table. So you can see here that the keywords of the electronegativity is the driver for the atomic bonding, and it is a measure of the tendency for the elements to accept an electron. The metals have a low electronegativity, and the non-metals have a high electronegativity. And that's what we can see actually in the periodic table. You can see that we are going to have the metals, which can be shown on the table here, okay, against the non-metals. The intra-atomic forces are the bonding force of the atoms. Some of these are going to be attractive and some are going to be repulsive. As the separation between the two atoms is going to be decreased. The attractive forces are going to be caused by the type of the bonding, which is related to the electronegativity. The repulsive is going to be the force stem from the electrostatic and the tendency for the like charges to repel, for example, the electrons from each atoms. The balance point between both types of the forces yields the interatomic spacing, and the net force may be zero, but the net energy isn't. And the net energy is going to be the bonding energy between the atoms. So the primary interatomic bonds are the ionic. The ionic bonding is found in compounds composed of the metals and the non-metals. The ionic bonds involve the complete transfer of the electrons from the metal atom, or we know it as a cation, and the non-metal, which is an anion. In the process, both cation and the anion achieve a complete valence shell configuration, and they are also respectively ions. The attractive force is relatively high due to the large electric charge difference between the atoms, and bonding energy is also large. The ionic bonds tends to form when the difference in the electronegativity is going to be typically more than 1.7. The covalent bonds tends to occur among the atoms located in the right-hand region of the periodic table, where the difference in the electronegativity is not especially high. The covalent bonds involve the sharing of the electrons between the atoms to achieve a stable valence configurations, and that is the respective electron orbital align through their motion. The bonding energies can be very high, but also can be quite low. Due to sharing, covalent bonds can form a double and triple bonds. The bond hybridization can occur, which make the covalent bonds very complicated. The covalent bonds tends to form when the difference in the electronegativity, especially typically between the 0.5 and 1.7. Now, the other type of the interatomic bonds is going to be the metallic. So when the metals combine with other metals, all the atoms unite their electrons, and we are going to have a sea or the cloud of the electrons swarm around the positive electron cation. The electrons are going to be delocalized, and when mean they can simply be drift under the thermal or the electrical potential gradients. The electrons also can serve to a screen or shield where the positive electron cation from each other, enabling them to remain connected. This property will enable the metals to be aplastically deformed. Bonding energies can be high or low, but are typically going to be lower for the ionic and for the covalent bonds. The difference in the electronegativity between the different metals is going to be usually negligible. Now we're coming to the secondary interatomic bonds, like the dipoles, the van der Waals, and hydrogen bonding. So the secondary bonds are much weaker than the primary bonds and fundamentally arise from the small electrostatic forces that exist when there are separated regions of the positive and the negative charge. Generally, these are going to be called the dipoles. Due to the presence of the dipoles, the molecules arrange themselves such as that the positive and the negative electrons regions are going to be aligned. The dipoles exist for many reasons, including the polarity caused in the high differences in the electronegativity between the atoms, or the presence of the non-bonding longs pairs of the electrons. The van der Waals forces stem from the distortion of the electrons orbital due to the dipoles. And the hydrogen bonds are unique secondary bonds that occurs due to the electronegative nature of the hydrogen. And obviously, the hydrogen must be present. So here we're going to discuss about the bonding force and the energy. So you can see in this table, from that table we can see that the first column is going to be about the substance, the second one is going to be the bonding energy, and the last one is going to be the melting temperature. The ionic materials exhibit a tendency for the high melting points, roughly in the line with the bonding energy. The covalent materials exhibit to a broad range of bonds energies and melting temperatures, and these materials tend to achieve the highest melting temperatures. The metallic materials exhibit a narrow range of the bonding energies which correlates with the melting temperature. The hydrogen bonding favor melting temperatures more than the van der Waals. Overall, the relationship between the bond energies and the melting temperature is going to be complex. Sometimes we may have a mixed bonding. So you can see in this diagram, that's the diagram on the A shows the bonding tetrahedron, where each of the four extreme or pure bonding types is located at one corner of the tetrahedron. So we're going to have three mixed bonding types are going to be included along the tetrahedron edges. In the shape B, the material type tetrahedron, where we're going to have a correlation of each material classifications like the metals, the ceramic, the polymers, and extra, with its types of bonding. We also can have the crystal lattices. So according to their size, like the atomic radius, the valence, and the bond type, the atoms of the materials will organize themselves into a repeating units, and we call the unit cells, which combine to form a crystal lattices. These are called the crystalline materials, and under unique circumstances, the crystal lattices can be observed on a macro scale. For example, a single crystals. More often, materials will exist as a combination of many small crystals of a given lattice structure, which we call the polycrystalline. To a significant extent, the lattice structure of the material gives a rise to its exerted properties. for example, the electrical conductivity, or the specific strength, or ductility. However, this can be complex to understand. The relationship between the crystal lattices and the metals is going to be less complex due to the metallic bondings. So let's cover the nature of the metals. So the metals are typically defined as an elements with a valence of +1 or +2 or +3. But the key characteristic of the metal relates to the bonding between the metallic atoms, specifically the presence of the metallic bonds. The metallic bonds is characterized by the sea of the free electrons that comprise a matrix that can hold the underlying metallic atoms together. The valence electrons of each metallic element are able to move away from their host atom and become dispersed over the whole volume of the solid. In this manner, the electrons are going to be delocalized and free to be influenced by external forces such as the heat or the electrical potential. Hence, the metals are going to be good conductors of the heat and electricity. The absence of the rigid bonding between the atoms will also facilitate the plastic deformation. Now, the nature of the metals of the lattice structure, well, all the crystalline materials except the specific lattice structure. And lattice structure has a strong bearing of the accepted properties, especially for the metals. The metals are typically either face-centered cubic, body-centered cubic, or hexagonal close packed. So again, for the videos, you can watch them through the view because I cannot. I actually even going to play them here. It's not going to be show you the video. Now the dislocation. So you can see here that in these two diagrams, the structure is not going to be uniform. It's going to have some dislocations to be shown off. So other than application of the stress, all the materials will tend to change shape. Specifically, is going to be the strain. In metals, the nature of the metallic bonding and the subsequent lattice structure enables a relatively high plastic deformations and is a virtually important properties. So when atomic bonding is going to be very strong, like the ionic, then the atomic planes within the solid will tend to cleave apart rather than flow. If instead the atomic bonding is going to be less strong, like in the case of the metallic, then the atoms can slip over themselves, leading to dislocations. The motion of the dislocations is a primary mechanism for the plastic deformation in the metals. A dislocation is an imperfection, and the lattice is characterized by the region of the severe mismatch in the arrangement of the atoms. Other applications of an applied stress dislocations emerge and progressively going to be propagate to the ends of the crystal where the mismatch in the positions of the participating atoms will yield in a slip step. And this is essentially going to be a plastic deformation on the atomic scale, which is going to be an extrapolated over the whole solids. And this mechanism accounts for the change in the shape due to the applied stress. So a unique property of the metallic bonding is the malleability and the ductility. The malleability is the ability to be deformed plastically, and the ductility is the ability to be deformed into a wires. Again, you can find this video available on the view page. I prefer that you can watch them from there. So let's talk about the nature of the ceramics. The elements of the periodic table can be categorized into a metallic and metalloid and non-metallic. So the ceramic are typically going to be compounds that form between the metallic and the non-metallic elements. The ceramics in general can also be identified by the presence of a very strong and rigid covalence or the ionic bonding. An example is going to be the alumina or the Al2O3, which demonstrates an ionic bonding between the aluminium and the oxygen atoms. As seen, the valence shells of each atoms is going to be completed through the exchange of the valence electrons. So the presence of the strong bonding between the constituent atoms hugely influences the properties of the ceramics. So for example, under the application of the applied stress, there is a minimal scope for the atoms to relocate, and that's what we call the poor dislocation motion. Hence, the ceramics tends to exhibit the brittle failure mechanisms. Under tension, the ceramic crystals will readily cleave, but strength under the compression can be very high. A consequences of strong bonding is also tendency for the high hardness, high melting temperatures, and poor electrical conductivity. The advanced ceramics, however, do exist, which can exhibit the broad range of the technologically relevant properties through a deliberate processing effort. Again, you can watch this video on the view and take some notes out of there. The glasses are closely related to the ceramic but differ in a critical way. The glasses are non-crystalline or the amorphous, whereas the ceramic are crystalline. This refers to the degree of the atomic scale organization. Specifically, the crystalline solids consist of a repeating atomic locations that extend for relatively a large distance throughout the solid. And this is called a long-range order and results in a lattice. Non-crystalline solids lack the repeating atomic locations, and so order is going to be limited to several atoms only. And that's what we call it the short range order. The bonding between the atoms is still strong, and so glasses can exhibit many of the same properties of the ceramics. However, the lack of the long range order tends to make the glasses weaker mechanically, but can provide benefits in the other ways, such as the optical transparency. By the way, there's another video here, can be checked on the view. The polymers are generally referred to as plastics and are composed of the long chain repeating molecules. Typically, a carbon comprises the basic skeleton for the involved molecules, but other elements can also be involved as well. The bonding between the atoms within each molecule is going to be typically covalent. which is going to be strong. But the bonding between the molecules is going to be weaker and based on the secondary bond types. An example is going to be the polyethylene. So come back once again to the question, which is what are the hybrids or the composites? So the composites are a class of a material that are going to be a combination of at least two different materials, but which poses properties that are going to be uniquely different from a constituted materials. There are many examples, both naturally occurring and synthetics. The timber is a natural composite, consists of a cellulose fibers held together by a matrix of lignin. Fiberglass is a synthetic composite consisting of glass fibers encapsulated in a polyester resin. The composites commonly take the form of either the coating or the additives in the matrices, for example, in the case of the fibers or the particles, or can be used as laminates. Many composites are used for the high-performance applications such as the aerospace components or in the sporting equipment. So this module summary will simply going to be summarized in the following learning outcomes. First, the students become familiar with the main material types, which are the families. Also, the student improve their understanding of the atomic bonding and the crystal structures. Finally, the student understand how the atomic bonding determines the differences between the materials and then demonstrated properties. Some important readings and references can be, for example, the Klister and Routledge materials of the material science and engineering, and also the Ashby materials selection and in mechanical design. And you can find the engineering materials by the Budinski and Budinski. So we're going to have a research topic for you, and we're going to try to have an example for that in the lab session. Mainly you can check this reference, this article, and natural impact of the impact resistance and the bacterial composites of the nanoparticle coating. And there's actually this video also can be watched, and this will give you a further information. In the practical session this week, we'll try to learn about the literature review and how to read a paper. So that's it for the week number 2, and we're going to see you in the class for answer your questions.